Freedom, who is playing a home game. And he will speak on strong homotopy bialgebras, coherent diagrams, and deformations.
If I get that far. So, was it? Okay, so I'll start with diagrams. So we're going to have two small categories. A function from the objects of A to the objects of C. And we want to describe functors extending that map on objects. So we seek functors from A to C extending F. Is that too small to be legible? Is that legible? Yep. Okay, so what we do now is we let En, or sometimes I'll write this as En of F, be the product over all strings of morphisms n long. So this is something in the nth level of the nerve of A, and we just look at hom from f of x naught to f of xn. And so the structure of this thing is as follows. We've got, it's an augmented simplicial set. E0, so E0 is just the, so you just take, so it's the product overall.
It's just the product of the automorphisms.
Product of the endomorphisms. Yeah, product overall, yeah. So we've got an augmented simplicial set. But as you can see, the numbering is a bit unusual, and I'm going to make the numbering even more unusual by, so what we do is we regard this as inner cosimplicial. So I'm going to, so this map from E1 to E0, I'm going to label as sigma naught. The maps from E2 to E1, sigma naught and sigma 1, the map going the other way is D1, and so on. And so we've got a cosimplicial set, except we're missing the two outer coface operators. And there is also a product on this. And this is just given by F cup G evaluated on this string x naught up to x m plus n is F evaluated on the string from xn up to xm plus n, composed with G going from x naught to xn. this is for, yeah, so for f in En, g in En. And properties that this thing has, so in addition to being co-simplicial, I suppose we've also, as well as this product, so this is associative, and we've got a unit in E0 just given by the identity for all x0. And so properties that this thing has of this product, well, if we look at di of f cup g, that's just di of f cup g if I is less than or equal to m, and f cup di minus mg for I greater than m. And now, and then for the sigmas, it's entirely similar. Sigma I of f cup g is sigma I of f cup g for I less than m, f cup sigma I of g for I greater than or equal to m. And what we now do is define the Malver-Cartan set and I suppose we're quite a long way removed from Ludwig Malver and Elie Cartan here, but f in E1 such that sigma naught f equals 1 and d1 of f is f cup f. And so one property you automatically have is that once we've got one of these elements, this thing actually becomes a genuine co-simplicial object. Because, so, omega and MCE gives operations En to En plus 1, so operations d0 and d operations d0 and dn plus 1, and that's from En to En plus 1 just by d0 of g is omega star g and dn plus 1 of g. Sorry, cup. Cup. Is g cup omega. And the condition, and this, so then E becomes co-simplicial. And the condition for this to do this is precisely that it lies in the Malver-Cartan set. And now, an exercise, and it's not a difficult one, so for EF as above, the Malver-Cartan set of EF is the set of functors from A to C extending F. And so you see what happens is that for each pair of objects, your Malver-Cartan element is defining a morphism in C. If we look over here, something in level 1 is just a, and then the two conditions there correspond to requiring that it maps the identity to the identity and that it's multiplicative. Now, so things like this form what I call quasi-comonoids. So a quasi-comonoid is a diagram of the sort we've just seen. So you've got this weirdly labelled augmented simplicial thing with unit and product satisfying the properties above. And if you want a formal definition, what we do is, oh yes, so hang on a minute, I better say, write QM star, or sometimes QM star set cross for the category of quasi-comonoids. And so the formal definition is that we first define delta in contained in delta to have objects M for M greater than or equal to naught, morphisms F from M to N such that F of naught is naught and F of M equals N. And this has a monoidal structure given by M plus N is M plus N. So it's contained in the ordinal number category. So it's non-decreasing morphisms with that property. And then, I suppose I could have squeezed it like this. And then what we're going to say is that a quasi-comonoid will just be a lax monoidal functor from that monoidal category to the one we're interested in. So a quasi-comonoid in some monoidal category C tensor is a lax monoidal functor from delta in plus, and if you don't like this definition, it's exactly the same as the first one. And so that I want to now explain the reason for this terminology. So if a strict monoidal functor, so yeah, so reason for terminology. A strict monoidal functor would have, so the maps from EM tensor EN to EM plus N would be isomorphisms. And the identity map from the unit in our monoidal category would also have to be an isomorphism. And then E1 is a comonoid because the co-unit is sigma naught from E1 to E0, which is 1, and the co-multiplication is D1 from E1 to E2, which is E1 tensor E1. And when these maps are weak equivalences, rather than being any map at all in the case of lax monoidal functors, or isomorphism in the case of strict monoidal functors, this is Leinster's comonoid up to homotopy. I think he almost exclusively works with monoids up to homotopy, but you just reverse all the arrows and you get the equivalent concept. Okay, so now examples. So we've seen quasi-comonoids in sets. Let's see what we get for quasi-comonoids in abelian groups where the monoidal structure is given by product, or direct sum if you like. And that is just the same as cosimplicial abelian groups. And the reason for that is that so we find that the unit has to be 0. The product has to be given by, first of all, zero also lies in the Malloy-Cartan set, MCE, so defines our extra cosimplicial operations, and then the product has to be A cup B is d m plus 1 to the NA plus d naught to the MB for A and EM. So it's Alexander-Whitney cup product with respect to addition. And then, in fact, MCE is just co-cycles in the cosimplicial normalization of E. So this is just saying that sigma naught is 0, and this, well, I'll write it out. A in E1 such that sigma naught A is 0, and then the other condition just reduces to saying d naught plus d2 minus d1 of A is 0. Now, a slightly more interesting example. So that was example 1. Let's look at abelian groups with tensor product. So what happens is any cosimplicial, so we have a map from cosimplicial non-commutative rings to that, simply given by setting A cup B to be the Alexander-Whitney product. dm plus 1 is rated n times d naught iterated. So that's and so the fact we can do that tells us that we can get these things from DG associative algebras. So DG associative algebras map to cosimplicial rings by, so it's Dalt-Kahn denormalization and shuttles. And that then maps to these quasi-comonoids. But that's an extremely inefficient way of writing it, because all we're really because the shuttles and Alexander Whitney cancel each other out, and all we've really got is that we just get, so the product on here is going to be given by di of A. So the denormalization is generated by symbols di times A subject to the condition that the alternating sum of the di's has to equal the differential we had back there. And we just get that this thing has to be dj plus m, then di applied to A wedge B. That's for A in AM, B in AN. So what we're actually getting is that a DG associative algebra is equivalent to a pair, well, I suppose the category is equivalent to the category of pairs A omega for A, one of these quasi-comonoids, and omega, a Maruc-Cartan element. Because, and this is where I'll explain the notation we're getting. So Maruc-Cartan applied to the denormalization we find is just 1 plus the set of A in A1 such that dA plus so we're back to
Is this equivalence just as regular categories or categories?
this is as categories. This is equivalence of categories, yeah. Right, so that's right, and now one important definition. So I'm going to define C star to be the constant quasi-comonoid. So it's the final object in the category. And lemma or exercise if you like. A map of quasi-comonoids from C star to E is just the Maruc-Cartan set. Right, so now we can start looking at homotopy coherent diagrams. So C be simplically enriched. And again, we have F from the object of A to the object of C. Now, we find that the equations we had before give us a quasi-comonoid in simplicial sets. And so we can then define MC, hang on a minute, yeah, MCE, a simplicial set by MCEN is MCEN. And we'll say that a map D to E in, so these are now simplicial quasi-comonoids, is a weak equivalence. And it's going to be the obvious definition if dn to en is a weak equivalence for all n. And now, yeah, I think this is worthy of a new board. So what we're going to find is that if we just right derive Malraux-Cartan, we're going to get homotopy coherent diagrams. So the right derived functor RMC, so this is going to be from homotopy category of simplicial quasi-comonoids to homotopy category of simplicial sets exists and is the space of homotopy coherent diagrams. A la Boardman vote. So right derived, we only need, so I've defined the weak equivalences, which is enough to determine right derived functors if they exist, because it just means we have a map from MC to RMC, such that with RMC mapping weak equivalences to isomorphisms, and it's the universal thing with that property. So the proof of this, having just said I didn't need the model structure to define that, I'll say there is a model structure. On these simplicial things. So fibrations are really fibrations. And what you find is that a cofibrant replacement C star tilde for C star. So C star being.
Sorry, yeah, but how do you know what? Can you work out what the vibration?
Yeah, it's just. Well, I've told you what the fibrations weak equivalences are. You just check it's got the universal property. It's got a lifting property.
So you know it's cofibrantly generated.
Yeah. Yes.
You're able to
Yeah.
explain what cofibration.
Well, but you can just, so the way you prove this exists is because it's cofibrantly generated, but you don't, but having told you fibrations and weak equivalences, that determines what these things are. It's just, it's the obvious, it's the Boardman vote thing. So you have C star tilde given in level n by n minus 1 copies of the unit interval, that's for n greater than or equal to 1, and star if n is 0. And x cut y is x naught y, the di's insert 1s, and the sigma i's take mins. And then that. So then you find that a map from this to E, which is exactly what we want it to give. So a map C star tilde to E gives, so we're going to have omega naught in E1 with sigma naught omega naught is 1, omega 1 in a line in E2, so it's a homotopy from D1 omega naught to omega naught cup omega naught, etc. And so this is saying that, so this omega naught is assigning a morphism to every morphism we had in A. This omega 1 is giving us a homotopy between the various what we want the composition to be and what it is, and so on. And so we've got exactly a homotopy coherent diagram. Right, and I'll just remark that this thing RMC, actually I suppose I haven't quite, right, I better just complete the statement. That's the right derived functor. RMC of E is the mapping space from C star to E, because since MC of E was simplicial hom from C star to E. But this is just simplicial hom from a cofibrant replacement to E. So it's what we want. And I'll just remark that RMC is in fact the right derived functor of E mapping to just MC of E naught, just because map is the right derived functor of just ordinary underived hom.
So E is automatically fibrant?
I think in this, that's a good point. So this is assuming E is, I think in the example I've given you, I think it is, but yeah, in general you have to take fibrant replacement.
Of course, we have a very specific.
We have a specific E, yeah. In general you would have to take really fibrant replacement of E. Usually it isn't a problem. But yes, so there is, I suppose because this thing isn't quite, because it isn't quite a cosimplicial set, it's not quite guaranteed that this will be really fibrant, but it's close enough that it's never too hard to check. And I think in all the examples I work with it is. Right, so now, algebras.
I'm sorry, but can you, I guess you don't want to say more about why C star tilde is cofibrant, but can you, that's the theorem. I mean,
yeah, that's the theorem. Just
you're
do
going
it.
to prove the proposition, and then you've more or less restated it by saying that that guy is cofibrant. So would you? I mean,
It's in there somewhere.
it's in there. Well,
Right. Take a category C. A monad T on C. And an object X. And what we're going to try to do now is classify T algebra structures. on X. And so, definition, I have a quasi-comoid UTX given by En is home from t to the nx to x. So this thing ends up looking very like the co-triple resolution, except it's missing the outer bits because we haven't specified an algebra structure. And so unit and co-unit, so unit and multiplication for the monad will give us our, will give us the coface and codegeneracies, and then the important thing is the product. F cup G is F composed with T to the NG for F in En, G in En, and another exercise. Maroc-Cartan elements of this just correspond to T algebra structures on X. And it's just, it's a definition almost. So a T algebra structure is a map from Tx to X, satisfying exactly the two conditions we've got for the Maroc-Cartan set. And now, proposition, hang on a minute. No, let's just go back a bit. So key thing to note, if we choose a Maroc-Cartan element, E becomes a cosimplicial set. And that is, what's the co-triple resolution? It's the co-triple resolution or Kolar construction. Right, so that's that. And it's also worth mentioning, and if there's time at the end, which there almost certainly won't be, I can go into more detail with some of these. So we can also do coalgebras. So a comonad gives En as hom X to bot X, and bialgebras. So if you have a distributive monad and comonad, so we've got, I can never remember which way around these things go, top and bottom. Then we just stick top on the right and bottom on the left. Sorry, other way around. What is it? Oh, is that the other way around? Yeah. I suppose now I'm using bottom, it has to be top, doesn't it?
Is bottom to the N? En.
So it will be, yeah, so we just take En is hom, top to the NX, bottom to the NX. So, example of a coalgebra sheaf on a site with enough points. Because your forgetful functor is the pullback to the sheaves on the set of points of your site, and then the condition for the site to have enough points is exactly the condition for that adjunction to become an adic. And so, example of a bialgebra, a ring sheaf, which is how I first got interested in these things. Right, so now, strong homotopy bialgebras. We have exactly the same picture we had for homotopy coherent diagrams. So, the right derived functor of Marie-Cartan of ETX is TJ Laders, or roughly TJ Laders. Space of strong homotopy algebra structures. And it's just the proof as before. Although the way he defined strong homotopy algebras was slightly different, so he didn't have the degeneracy conditions. And I think he took concatenation rather than min. But it's clearly homotopy equivalent. Right. So now, there was a problem that he had, which was define morphisms. So he was only able to define the morphisms between strong homotopy algebras when he was working over some quite special operads, but he certainly couldn't do it for arbitrary monads, even though he could define algebras for strong homotopy algebras for an arbitrary monad. And the solution is just to combine these two approaches. We know how to do diagrams, we know how to do homotopy coherent diagrams and strong homotopy algebras, so we should be able to do both. So, solution, combine algebras and diagrams. And so, definition, given a simplicial set K and a map from the vertices of K to the objects of a category and a monad T on C, define En F T by product over all x in Kn hom Tn f of the first vertex of x, so d naught to dnx, mapping to the final vertex. And so what you should notice is that when K is just a point, this thing is ext if x is f of star. And when K is the nerve of A and T is the identity, EFT is EF. And then we have an exercise which the same as the previous ones. So the Marat-Cartan elements of this thing, of EFT, are diagrams from the fundamental category of K to the category of algebras in T, extending F. So that's the fundamental category. And so then that means, so define. Yeah, so now what we do is look at MC CTN to be a disjoint union over all such maps from delta n naught to objects of C, derived MC of E F T. And so this is a candidate for, so if we think of the underived thing, that's the nerve of the category. So replacing RMC with just MC, this is BN, so it's the end part of the nerve. And now comes a proposition, which is the simplicial space so MCCT naught, MCCT 1, and so on, is a Siegel space. And so the idea of the proof look at categories enriched in set to the delta in, and you put model structures on those things and get this thing out as a right derived functor. And so what we've done, so therefore we've got, so given a simplicial category and a monad, we've constructed a Siegel space. So we've gone from a monad on some form of infinity category to some other form of infinity category. And in fact, in all these constructions involving monads, all we've really needed is that it's a quasi-monad. So we could do the same for simplicial category and a monad up to homotopy, or even, I can't quite think why you'd want to do this, but it might be worthwhile, the quasi-monad. Right, so now I'll explain how this ties in with derived deformations. So we'll start by, so deformation functors are left exact, lex functors on commutative rings, usually sub-Artinian conditions, and probably working with some base. Derived deformation functors are left exact functors on simplicial commutative rings. And what this construction enables you to do is to get these derived things straight from data on underived things. So given a functor from commutative rings to categories, we can form something from simplicial commutative rings to simplicial categories by same object, and just hom underline C from x to y. A in level n is hom C x y a n. And so, typical example, C of A will be flat A modules. And usually you're working over local rings, so flat is the same as free, or Artinian rings even, so flat is the same as free. And then, say we have a given a monad top on C, for instance. If we want to study moduli of affine schemes, we'd look at the symmetric functor. We can then cook up a simplicial quasi-comonoid so we get E xt functor from simplicial commutative rings to quasi-comonoids in simplicial sets. So this is for just so you might, this would be like fixing the rank of your module. And of course, because we can do bialgebras, there's a similar game you can play if you want ring sheaves. And then MC ext maps from simplicial commutative rings to Siegel spaces, and the heart of this is derived moduli stack. So it's parameterizing the strong homotopy algebras. And the important thing is that this is incredibly general. You can do it for any monad, so you don't need to work out what sort of model structures you want on your derived objects or anything like that. And I will just mention that, so given omega in MCEA, look at the tangent space. So the tangent space of omega at omega of E is now a map from let's just stick with commutative rings for now. Commutative rings 2 quasi-comonoids in abelian groups with product, which remember is equivalent to cosimplicial groups. And this will then give us co-triple cohomology. So, for instance, Hochschild, Andre Quillen, I suppose it's generalized Andre Quillen. So we know that this construction is giving us the tangent spaces we want. And the derived thing, but just by general arguments about derived functors, we know that the derived Marais-Cartan construction applied to these tangent spaces has to just give us total complexes. So we know that the tangent spaces of these derived things will be the cohomology with theories we want. So we know it's the answer we were looking for. And yeah, that's.
Questions? Remarks? You finished the paper as well?
Is there a relationship between the notion of quasi-comonoid and Smith-McClure's notion of box-monoid or cosimplicial?
So I think,
is it dual or?
if I remember rightly, I think theirs had the outer operations as well. So I think theirs corresponds to one of these together with a Marais-Cartan element. Although it is a very long time. So I think theirs is genuinely cosimplicial or genuinely simplicial, isn't it? I think. So you know, I was saying that if you have one of these together with a Marais-Cartan element, then you get a genuinely cosimplicial thing. That I think is then there would be a box cohomoloid, I think. But of course, these things allow the possibilities of empty moduli spaces, which is something that the other stuff doesn't.
Other questions? I have a question about the definition of sheaf.
About the okay, so it's
Well, let me ask the question before you get the answer. So, a sheaf is an algebra for this Godemar.
co-algebra.
Co-algebra for this Godemar co-monad.
Yeah.
But you can do this for any cover of the tuples.
And
With values in 2 categories, 3 categories. So you get some sort of definition of homotopy sheaf. It should be closely related to various definitions of high stacks.
yes.
That's my question.
So I suppose, yeah, well, I suppose to do it as a sort of fit it straight into this construction, you'd have to have an honest. Well, no, I suppose you could. So the way I tend to think of it, you just look at. So you have x prime a set of points. U x prime to x. And that's a comonadic adjunction, which is precisely the same as having enough points. But I suppose there are constructions for any homotopy comonad, which I think is what you'd probably have to use if you're using more general points. Is my guess. So yeah, I think.
All right, so
Was a monad.
The dual motion. Quasi-monad. Okay. A monad is a monoid in the category of n-node functions in C with monodal structure given by composition. And so you just take the definition of quasi-comonoid, take the opposite for one, that's a quasi-monoid. So you end up with, you have a sequence T0, T1, T2 and so on. And these things are going to, it's going to be augmented co-sequential. And so on. And you're going to have, so it goes the opposite way. So T0 mapping to the identity. And that's going to be an equivalence T2 mapping to, and so on.
Different from the monad.
It's exactly, so this, if we're requiring these things to be, oh sorry, quasi. So quasi these things don't have to be equivalences. For monad up to homotopy, you're imposing the condition is equivalences. I have no idea whether, my guess is that quasi-monad is getting a bit too general to be useful, but you never know.
If there are no further questions, let's thank the speaker again.